So the topic is linear programs. So basically linear programming is I mean it's a really an interesting topic because it's a technique that can be used to prove things about many optimization problems. So it's super versatile. You can take many different problems that look like they have nothing to do with linear programming, and often you can kind of either transform them into a linear program or relax them to a linear program. And sometimes the solution to that linear program can actually give you, well, it'll often give you like an upper bound or a lower bound, and like sometimes it's actually going to give you the right answer. So yeah, this is kind of going to be a general technique that can be applicable to many different problems. One thing is like this word program. This is not, when I say, like, I don't know why they call them linear programs. I think this is this goes back to like a long time ago before they had computer programs. So like, these are not computer programs. They're like, yeah, anyway, a linear program is a type of optimization problem. So here's the setup. So you've got n variables. So x1 up to xn. So let's say these are real numbers, so they're real variables. And let ci, aj, and bj for I between 1 and n, and j between 1 and m, be real numbers. So these are fixed real numbers. Okay. So the a's, the b's, and the c's, those are just numbers, right? And then x1 up to xn are like variables that can change. So a linear program is an optimization problem of the following type. So we want to, let's say, maximize c1 times x1 plus c2 times x2 plus ... up to cn times xn, subject to the constraints that like a11 x1 times x1 plus a12 times x2 plus ... up to a1n xn. And like, okay, I'll just write another one. So like a21 x1 plus a22 x2 plus ... to a2n xn. Oh, sorry. On this first line, I meant to write is at most. On the next line, I've got some kind of linear combination of, x1 and x2 up to xn is at most b2. And this goes all the way down to am1 times x1 plus am2 times x2, ... up to amn xn is at most bm. Okay. Notationally, it's a little bit awkward to write down. But the key idea is that here we are maximizing a linear objective function, meaning, so if I think of the x's as being my variables, right? This is just a linear function of the variables. So it's a linear objective function. Subject to m linear constraints. Okay. So when I say linear objective function, you're not allowed to have like x2 squared, right? That's not linear, right? You need just linear function of the variables. And yeah, each of these is like saying some linear function of the variables is at most some number, right? So as an example, actually, maybe I'm going to write this example over there because I'm going to come back to it over and over. So as an example, we could have maximize 2x minus y subject to the constraints that x plus 3y is at most 3, is at most 2, x is non-negative, y. Okay. So here, okay, over there I was calling my variables x1 up to xn. Here my variables are like x and y, right? Okay, so this is an example of a linear program. Note that, okay, over there I had all of the inequalities going the same way. Like, you could, I mean, in general, you could like have your inequalities going different directions. It doesn't really matter though, right? Because saying that x is at least 0 is the same as if I multiply by negative 1 on both sides. That's the same as saying negative x is at most 0. So if you ever want to like flip an inequality, you can just multiply both sides by negative 1, and it's like equivalent, right? So of course, like this, yeah, this could be written as negative x at most 0 and negative y at most 0. Another thing is that, okay, so far we've just been talking about maximization problems. You could also, like linear programs can also be minimization problems, okay? And it's just the same kind of form. And of course, like a minimization problem, like it's kind of the same as a maximization problem because, well, if I just multiply the objective function by negative 1 and minimize it, that's the same as maximizing the original objective function. Okay. So obviously it's going to be way too cumbersome to keep writing. Like if I want to talk about a general linear program, I don't want to write all of this stuff. So we usually write a linear program in the form. So I write like C transpose times X, maximize, let's say, or minimize, whatever, subject to A times X at most B. Okay, where like C is the vector that contains like C1 up to Cn. A is the matrix A11 up to A1n down to AMN and AM1. And B is just the row vector, or sorry, column vector B1 up to BM. Okay. So this is like a much more kind of compact way of writing the same thing as this. Maybe I should say, what do I mean by like, because a times x is a vector, right? So, so we kind of need some kind of meaning for this statement. So here, like, if I've got two vectors, so for vectors y and z, you know, writing y is at most z means y and z have the same length. Because we can't compare vectors of different lengths. It doesn't make any sense. And yi is at most zi for all I. So the ith coordinate of y is at most the ith coordinate of z. So yeah, if you kind of think about what this is saying with these, with C being this vector, A being this matrix, B being that vector, it's actually saying the same thing as this, maximizing this subject to these M constraints. Any questions about that? Okay. Right, so generally if I'm talking about a linear program, I mean any kind of optimization problem that has this structure. Or it could be a maximization. This inequality could be switched. But like I said, that's just like multiplying by -1. Okay, so here, maybe just to drive this home, in this example, we would have C being the matrix 2, -1. Maybe I should say what the variables are. So the variables would be, you know, x and y, right? C would be this. The matrix A, you can just get it by reading off the constraints, the coefficients of the constraints, but you have to be careful. So, so the A would be like 1, 3 from those, from the first constraint. Second constraint, I've got like a 1 and a -1. My third constraint, I need to be careful because I have to be consistent, right? I need to, if I'm doing less than or equal to signs, I need to do that for every row. Otherwise, it's going to be wrong, right? So this one should be like a -1, 0, and 0, -1. And then B is going to be 3, 2, 0, 0. Okay. I feel like I'm going a little bit fast, but is it clear how this this example kind of breaks down, right? Okay. Okay, so like I said, really, I mean, the way I want you to think about linear programs is as a tool, right? What I want you to do is like think about how do you, so when you're given an optimization problem, it's going to be valuable to be able to translate that optimization problem into a linear program. And then we're going to use the fact that linear programs can be solved efficiently. Okay. I'm not going to prove that they can be solved efficiently because that's a little bit, yeah, that would take, to be honest, that would take too much time. But yeah, you can use the fact that they can be solved efficiently. So like I said, I'm not going to give you an efficient algorithm for solving linear programs, but let's talk about an algorithm and like build up some intuition about how these linear programs work. Right, so generally the feasible region of a linear program is the set of all points that satisfy the constraints. So it's the set of all x in R to the n such that AX is at most B. Okay, so when I guess when I'm saying NLP, I mean like the feasible region for this, let's say this linear program, right, is just the set of all x that satisfy the constraints. Okay. So to start getting some intuition about linear programs, we can think of things quite geometrically. So in this case, so you could check, but so these things are particularly nice when you're dealing with like just two variables like x and y. You can just plot the feasible region, right? So, so it turns out that the feasible region, meaning the set of all x and y that satisfy all four inequalities, is just going to be, it just looks like this. So okay. So this is like, I mean, something you probably did in high school or something, plotting like systems of inequalities, right? So yeah, you could plot this, and this is the region you're going to get. And if you think about it now, okay, what does it mean to maximize this this objective function subject to these constraints? Well, you can think of all of this very geometrically. So I want to maximize 2x minus y. I want to make that as big as possible. Suppose let's write down something like 2x minus y equals alpha or something. So what I want to do is I want to pick the largest alpha such that such that there's some x and y that satisfy 2x minus y equals alpha, and x and y satisfy the inequalities. So I want to pick a point in the feasible region that maximizes 2x minus y. If you plot this with, let's say, alpha equals 0, right, then that's just the line. So okay, I can rewrite this as y equals 2x minus alpha. So for any choice of alpha, this is just the line where the slope is 2 and the y-intercept is negative alpha. So if alpha is 0, let's say, then I would have this is the line corresponding to alpha equals 0, right? And as I increase my alpha, this y-intercept goes lower, right, because it's minus alpha here. And you can think of that as like I'm shifting this line to the right. So as alpha, so this is alpha equals 0, alpha equal to, I think, 2. So it'll have the same slope for every alpha. I think like this is the line alpha equals 2, for example. I think this should look a little bit steeper, but okay, so if you think about it, maximizing this thing is just trying to shift this line as far as you can without missing the entire region, right? If I draw the line over here, well, there's no feasible points on that line, right? So you want to shift it as far as you can while you're still touching the feasible region. And okay, if this drawing is in any way accurate, then it's kind of clear that this is actually going to be the point where it's maximized. Like if I keep shifting this line, what's the last point on the feasible region that is touched, where this line touches the feasible region, right? And I think it's going to be right through here, right? And I think this is at alpha equals 17 over 4. So like the maximum is going to be 17 over 4, where x is equal to 9 over 4 and y is equal to 1 over 4, right? Is that like geometrically, does this make sense? So more generally, you're going to have more variables, right? You're in a higher dimensional space. You have kind of, this is called a polyhedron in dimensional space. Your objective function, if you set it equal to some value, that just corresponds to some kind of hyperplane. And you're just pushing that hyperplane as far as you can while you're still touching the feasible region until it, at some point it doesn't touch and you want to look at the last place where it touches, right? Okay. Any questions about that? Okay. Of course, if this is like if I've got 17 different variables here, I wouldn't recommend trying to plot this in 17 dimensions and move a hyperplane, because you're not going to be able to visualize any of that, right? So we do have to kind of think of this in more generality. Okay, so there's this famous method for solving linear programs called the simplex method. Have any of you heard of or used the simplex method before in any course? You have? Okay. Okay, so then that's kind of nice. It's new for a lot of you guys. But that being said, we're not going to really use it in specific, like if this was like a second year course, I would teach you the simplex method and I would make you use it on like 10 different examples and stuff like that. We're not really going to use it on any examples, but I think the kind of rough idea, the intuition is kind of important to understand. So but since I'm not actually going to make you use it, I'm not going to really I'm not going to do any examples of it either. But here's a rough idea of the simplex method for solving linear programs. So LP just stands for linear program. Well, actually, this whole simplex method, I feel like it's a fancy way of saying something that you actually are already familiar with, which is just the concept of like gradient descent or gradient ascent, or like in calculus, have you heard of this kind of idea? You want to maximize some function, start somewhere, and like now look at the derivative at that point and walk where the derivative's going up, right? And now you're at another point. Now I'm going to look at the derivative and walk in the way that the derivative goes up. And that should get you to a higher value, right? Now, of course, you could be stuck in some local maximum or something. But actually, like in linear programs, we're just dealing with linear functions. There are no local maxima, right? So in some sense, when we find a local maximum, that's a global maximum. Like you can't get, there's no kind of getting stuck in some local maximum. It's a linear function, right? So basically the idea is similar to gradient. So let's say we're doing a maximization problem, so I'll call it gradient ascent. So we're going to basically search for a local maximum. But since it's a linear function, there aren't really basically a local maximum should be a global maximum. It also requires the feasible region to be convex, which we're going to talk about in a second. But anyway, it is convex. So anyway, so let's search for a local max, which will turn out to be a global max. So basically the idea is like this. Pick a starting point x naught in the feasible region. But this step is actually subtle, because how do you even do that? Like, if I've got 17 variables and 100 constraints, how do I even find even one point in the feasible region? That's not clear. So this, we're going to have to come back to this. So this is subtle, that it's not even clear how to find even one feasible point. But let's suppose that we can. Okay. Do you see why that's kind of subtle? Like, how do I do it? I mean, it's not clear that maybe there are no feasible points, right? And how do you even detect that? But yeah, we'll talk about that in a second. But suppose you can start somewhere. So I don't know, in this kind of picture we had over there, yeah, I could start at some x naught. And then, move in the direction of the gradient. What do I mean the gradient? The gradient of the function C transpose x. Like, this is our objective function for the linear program, right? But actually, like, this gradient is not very interesting. Can anyone see what it is? Like, you remember what gradient is? I take the derivative with respect to x1, right? What's the derivative of this with respect to x1? Yeah, in this case, it's going to be 2. Yeah. Just c1. Yeah. So the first coordinate is just the derivative with respect to x1, c1. Second coordinate is c2, c3. So it's just c. So the gradient of this objective function is just the vector, right? So I just want to move in that direction. In this example, our vector was 2, -1. So that tells me I want to move in the direction, yeah, like kind of to the right by 2 units and down 1 unit kind of thing. I want to move that way. And you should just, and this gradient doesn't actually depend on x, right? It's just a vector. So yeah, it doesn't change as x changes. So everywhere the gradient's the same. So what I should do is I should just keep walking. Let's say it's kind of like this. So I'll keep walking, right, until I hit the boundary of the feasible region. Okay, now I'm at the boundary. But what I could do is then look at this kind of line that I've hit. This is like a hyperplane in my feasible region or something. Like so I could then take my objective function restricted to this line and compute the gradient inside that line. Like, I could just say I'm in this space, and what would my objective function be? And I compute the gradient again. And so then I just kind of move either to the left or to the right. It's going to turn out that the gradient, I think, was going to tell me to go this way, right? And then now I'm at this point. So yeah, when you hit the side, when you hit a hyperplane, let's say, on the boundary. None of this is, like I said, this is a rough idea of the simplex method. Yeah, basically, once you hit some kind of hyperplane, you restrict the objective function to that hyperplane, and you compute the gradient, and you walk in that hyperplane. So restrict my objective function to the hyperplane. And do gradient ascent within it, right? Which is what I'm doing here. But now, actually, I've reached kind of a corner of my feasible region. And now I can't actually, like there's no direction to kind of move around. So you keep doing this until you reach, eventually you reach a vertex of the feasible region. So eventually you reach a vertex, or you might think of it as, like in this picture, like a corner of the feasible region. Now, that's not necessarily the best option, right? We actually know that the function is going to be optimized at that corner, so I'm at the wrong vertex. But now what you do is you just like kind of look at all the possible neighboring vertices on the feasible region, and if there's one of those neighboring vertices that I can move to in a way that increases my objective function, I just go there. So try to move to an adjacent vertex. Adjacent meaning like there's like a kind of line between them on the feasible region, while increasing the objective function. If you can't, then actually this is you found the local max. So if you can't, then you found the local max. And because everything is so nice and linear, then actually the local max will be a global max. Oh, and actually, when I say increasing here, I mean strictly increasing. Okay, that's somewhat important because you don't want to come back to the same vertex you've seen over and over and over. At this point, I should admit, no one's actually taught me the simplex method properly, and I've never actually tried to use it by hand. But I think this is what it is, right? You keep doing gradient descent, you hit a wall, you do gradient ascent in that wall, and eventually you hit a vertex, like eventually after doing this maybe many times, and then you're at a vertex, and I want to move to another vertex that has a higher objective value, strictly higher, and you can kind of detect that and move in that direction. And the thing is, you'll never come back to the same place because you're always strictly increasing at every point. So now, this is a method that can always work to solve a linear program. I should also say, I'm also missing there are some subtleties here that the linear program could be unbounded. Like the max could be infinity. Maybe you can just, maybe it shoots off to infinity in that direction or something. During this thing, you have to also detect that, which, yeah, I'm not going to maybe say anything about. But yeah, basically, this simplex method can be used to solve linear programs, but it's not an efficient method. The reason is that your feasible region might have exponentially many vertices on it, and the simplex method may travel around to like exponentially many, like exponential in the size of in n and m, for example. It may actually travel to exponentially many vertices. So it's not generally a polynomial time algorithm. Any questions? Okay. Oh yeah, I said we're going to come back to the starting point because none of this makes sense unless you can even find a feasible point. But there's a trick for that. the trick is actually before you even start trying to solve the linear program that you're interested in, you use the simplex method to solve a different linear program, which will give you a feasible point if it exists. So suppose like, so how do we find the first feasible point? X naught, right? So what you can do is solve, well, solve a different LP, which is going to ask you to minimize a variable which we'll call t, subject to, let's say, 1, x1. So basically, I'm going to put all the constraints that I would normally have in my linear program, but I'm just going to add some slack over here to make it easier to satisfy. Oh, and maybe I'll say t is at least 0. So this has n plus 1 variables because I've got x1 up to xn like I had before, and I have t, a new variable, and m plus 1 constraints. Okay. Now the relevance of this is that, so I can try to, let's try to solve this with the simplex method, and I claim it's trivial. Well, not trivial, I mean it's easy to find the starting point for this one, because I can just set, for a starting point for this linear program, I can just set all the x's to be 0, right? And I just, maybe some of these b's are negative, I just make the t really big. And I've got a positive number here and 0 here. So for this linear program, I can easily find a starting point. And then I can solve the linear program with the simplex method. And if it outputs t equals 0, like if I get to the optimum and t is equal to 0, and then the x variables will satisfy my original linear program. Like if I can get t to be equal to 0 in this thing, then it's actually just giving me a feasible point for my original linear program. So that's kind of clever. So this one, it's trivial to find a starting point because I just set the x's to 0 or something. I picked t to be really big. But yeah. Is that clear? So I could do the simplex on this thing to find a starting point for this one, and then I can run this one, basically. Any questions about that? Yeah.
What happens when you can't?
Yeah. That's something I should have said. So, yeah, if you solve this linear program and it says, the minimum t is 0.1. Yeah, what does that tell you about the original linear program? Well, it tells you that the original constraints that you had when there was no t here, they just cannot all be satisfied. Right? Because if it tells me my minimum t is 0.1, then if I put t equals 0 in here, it must be impossible to find x's that satisfy it. So that would mean that the original linear program was infeasible. So I probably should have defined that before, but yeah, a linear program is infeasible if its feasible region is empty. If it's feasible region, which was defined over there. So indeed, if t was not equal to 0 in this thing, it would tell you your original one was infeasible, which tells you you shouldn't even try to find a feasible point because there are none. And if you have a infeasible linear program, which is a maximization problem, then the answer is just negative infinity or something. Okay. Any other questions about that? Okay. I said the simplex method, it's a very popular method. You should be aware of it. We're not really going to use it. But it's not it doesn't give you an efficient algorithm. Okay, and I'm also not going to present an efficient algorithm for linear programming in this course, but we're going to use the fact that it exists. So this was a theorem first proved by Kachin, that there is a polynomial time algorithm for solving linear programs. Okay. The original, so just a kind of a reference for you guys. Like there's something, the original proof was via something called the ellipsoid method. But now there are kind of fancier, well, not fancier. Actually, the ellipsoid method is actually kind of complicated. Now there are simpler methods called interior point method, which also give polynomial time algorithms. But like I said, we're not going to go into the details. Okay. Instead, our focus is mostly going to be on, okay, I'm going to give you like discrete optimization problems, and we're going to like transform them into linear programs. And then we can say, if I can do that, then I've got a polynomial time algorithm, because you can solve every linear program in polynomial time, right? So we're going to look at the kind of reducing things to linear programs, and then we can just say, we can hit it with this hammer and say it's polynomial, right? Okay. Any questions about any of this? Okay. Oh, by the way, it's not even completely clear at first, I think, when I write down a linear program, why would this be in a course called Discrete Optimization? Because it's not very discrete, right? We have infinite, our domain is infinite, right? It's a polytope or polyhedron. But now if you think about the fact that it has to be optimized at one of the kind of corners of the polyhedron, then it's kind of clear that it is kind of discrete, right? There are finitely many choices. Yeah. Okay. So everything so far has been quite rough. Let's actually do some rigorous stuff. Okay, so one important thing about linear programs is that they are something which is part of a more general theory of convex optimization problems. Okay, so it's important to know what a convex set is. So a set C in Rn is convex if for all x and y in C and lambda between 0 and 1 we have that the point lambda x plus 1 minus lambda y is also in C. Okay. This is maybe a kind of standard definition. What it really means is if I take 2 points that are in C, like what is this lambda x plus 1 minus lambda y? I mean, that's really just like a point on the line segment between x and y. What this is saying is that if I take x in C and y in C, then all the points on the line segment between them are also in C. Okay, so like examples are like a circle, right? A circle is definitely convex. If I take 2 points in the circle, the line segment between them is inside the circle. If I do something like this is not convex. Like I made the points inside of this shape because if I took x and y here, the line segment goes outside, right? Also a donut like this, not convex. Okay. So an important thing in linear programming is going to be the fact that the feasible region is convex. Okay. So for a subset of Rn, the convex hull of S, so the notation is, so I'll just write conv and then S. Okay. So basically if I have a bunch of points in Rn, I want the convex hull to be like the smallest convex set that contains all of them, which in other words is just the intersection of all the convex sets that contain S. So it's like the intersection over all C that's a subset of R to the n such that S is a subset of C and C is convex of C. Okay. So yeah, this was my set S, this thing that was not convex, right? The convex hull would probably be something like, where this is like a straight line. Yeah, totally, yeah. If any of you've seen that when you put plastic wrap around something and suck out all the air, yeah, what does it end up as? Yeah, that's a good analogy. Okay. So when we're talking about linear programs, I was talking about like corners and vertices and stuff. Let's give a proper definition of that. So for convex set C, say that a point Z in C is a vertex. So, okay. Unfortunately, it's the same word as we use in graph theory, but yeah, you should think of this differently. So a vertex of C, if there does not exist x and y in C with x not equal to y and some lambda in the open interval 0, 1 such that z equals lambda x plus 1 minus lambda y. Okay. So actually, like these pictures, like a circle, there are no vertices in a circle. But if I draw something like some kind of thing like this, so a square is convex. Take any 2 points in the square. The line between them is in the square. And this would be a vertex because at that point, there's no way to take 2 points in the square such that this point is like strictly between them in their line segment, right? I can't put a line segment around that point and keep it inside the square. It's just not possible unless the line segment starts at that point. But that's like, yeah, that's being excluded from this definition. So this would be like a vertex. Okay. Yep, you could also, yeah. So this lambda is doing that, but like you could also, yeah. But you could also make this a closed interval and just say that z is also not equal to x or y. Yeah. Yeah, different ways of saying it. Yeah.
You said that a circle doesn't have vertices. Wouldn't the whole boundary be vertices, though?
Actually, you're right.
Force lines.
Yeah, everything on the boundary is a vertex. So the opposite of what I said is true. Single point on the boundary is a vertex. You're absolutely right. Because like a tangent line somewhere, it's going to stay completely outside of the circle except at that point, right? Or it doesn't have to be any line. You're not going to be able to keep it inside the circle. Yeah. Any other questions? Mistakes to point out? I'm glad when you point out mistakes because it like shows that you're, yeah, following. Okay, so we want to talk about linear programs. So let's kind of bring this back to that. So I want to define something called a polyhedron, which is just like the feasible region of a linear program. So polyhedron is a set of the form like all x in Rn such that ax is at most b for some m by n matrix A and some b some vector b of length m. Okay, so that's, yeah. So in other words, like the feasible points for a linear program is a set called a polyhedron, right? This is just coming up with a word here. Here's a lemma which is not hard to prove. Polyhedra are convex. Okay. So I'm not going to prove this, but it's kind of actually clear from the definition, by linearity, basically. Like, if I take two things in this polyhedron, and I take lambda times 1 and 1 minus lambda times the other, and I take a times that combination, you can kind of, everything's linear. You can pull the a inside. Each of them will be at most b, and then you have lambda b plus 1 minus lambda b. That makes b, and yeah, so it's all fairly simple. Okay, so now I want to give you sort of an algebraic definition of what the vertices of a polyhedron are, right? So a way of kind of determining if a point, a feasible point is a vertex or not. Okay, so I need a definition. So let P, so it's the set of all x such that AX is at most B, be a polyhedron. So for some Z P, define, or like for any point in P, define AZ to be the matrix where a row, so let's say a row AJ of A is in AZ, so it's like it appears as a row of AZ, if and only if AJ times Z is equal to BJ. This probably requires some explanation. Right, so I think of this like the inequality that defines the polyhedron. Like that's a system of m constraints, right? Because let's say A is an m by n matrix, and this is a length m vector. So yeah, this is, I've got n variables, I've got m constraints, and those are all inequality constraints, right? If I pick some z in P, some of those constraints might be strict inequalities, and some of them might be equalities. Okay? And all I'm doing here is I'm saying AZ, like I look through each constraint so this is like a subscript z here. So for this specific z, I look through each inequality. Each of them is either strict or equals, and I just take the ones that are equals, and I just make a matrix out of those. Is that clear what this means? So I'm looking at, so this is like one of these constraints. Usually it would say this, but I look at the ones where it's equal, and I put that into my matrix. Well, I put that row of A into the matrix. In some sense, I don't really care that much about the B, other than the fact that, yeah, it's a tight inequality. Okay. Okay, so I'd like to now classify the vertices of a polyhedron in terms of these matrices AZ. So this is a lemma. So P is like in the definition, so let Z be an element of P. So then Z is a vertex of P if and only if the matrix AZ has rank n. Okay. We're just like everywhere else in this lecture, n is the number of variables, like it's the length of x. This is length n. Any questions about that? So I actually like, yeah, in some sense I don't really care. It's not really that important how many rows AZ has. Like, okay, if it has rank n, it must have at least n rows. But yeah, the important thing is like, I mean, actually, you can think of this intuitively. Like, suppose you take a point in the polytope. If none of the constraints are tight, I can sort of just move any way I want without violating a constraint. If I move just a little bit, I can move any way I want, right? But if I move too far and I hit a wall somewhere, like, you know, you hit some kind of plane on the boundary of your thing, that means that some constraint must have become equals. But if that kind of wall still has high dimension, like dimension bigger than 0, I could just walk around in that wall, right? Until I hit another 2 walls, and then now I've dropped my dimension by 2, right? So essentially, like if you're in n-dimensional space, you should, if you're a vertex, you must have sort of run into like n different kind of walls in some sense in order to be a vertex. Like you must reduce the dimension by n. And yeah, like, but the thing is, the rank is what's important, because I could have 2 constraints, for example, that are the same, like 2x minus y at most 3 and 2x minus y at most 4. I mean, oh no, that's not quite what I wanted to say. But in any case, there could be some redundant constraints in here. If anything's redundant, then it doesn't make a difference. So you should, yeah, really what matters is if this has rank n. Anyway, let's prove this. Okay, so for one direction, let's suppose that the rank of AZ is less than n. Okay. By the way, the rank can't be bigger than n because this has n columns, right? So it's either equal to n or less than n. So, okay, what I have to do in this case, I need to show that Z is not a vertex. So I need to find a certificate of that. I need to find X and Y such that Z, you know, I want to observe that Z is on is on one of these line segments where X and Y are in P, right? So I need to find this. Okay, here's how I'm going to do it. So this means if the rank is less than n, then there exists a non-zero. So by the rank nullity theorem, if the rank is less than n, then the kernel must have dimension bigger than 1, or at least 1. So there's some non-zero w in Rn with AZ times w equals the 0 vector. So put a vector thing to, it's a zero vector. So this is by rank nullity. Okay. So what I want to do is basically just make my x to be equal to like z plus epsilon w, and my y to be like z minus epsilon w for some very small epsilon. I need to be a bit careful though, because yeah, I need to show that these are in the polytope. But here's how I'm going to do it. So for any row, let's say aj of A that is not in AZ, well, for any row that's not in AZ, we know that the inequality is strict. So AJ times Z is strictly less than BJ. So if I take Z and I perturb it very slightly in any direction, I can still get that this is a strict inequality. So in other words, kind of by continuity, like, so, you know, there exists some epsilon j such that, which is positive, for any, let's say alpha between 0, strictly bigger than 0, strictly less than epsilon j, if I a times z plus, well, plus or minus alpha times w, it's also going to be less than bj. So I can pick a small enough epsilon such that if I add a multiple of w, which is with a coefficient alpha, which is less than epsilon j, as long as I make this epsilon j small enough, all of these perturbations are going to also satisfy the inequality. Okay, now I just let epsilon be the minimum over all j of my epsilon j's. Okay. And I'm going to define x to be minus epsilon w and z plus epsilon w. And I claim that this choice will be my certificate that Z is not a vertex, right? Because so Z I can write as 1/2 x plus y, right? If I, well, in other words, it's 1/2 x plus 1/2 y. Oh, and by the way, since w is not 0, right, it's a non-zero vector, we know that x is not the same as y. And yeah, if I just add these things together, right, I get 2 times z. The epsilon w's cancel. So yeah, z is really like the average of x and y. And also, yeah, x is going to be in the polytope because, so for any row, let's say aj of A, we have that, so either, you know, either this row is in AZ, so if AJ is in the matrix AZ, then we get AJ times X, let's say, equals AJ times Z minus epsilon W. Which is, if you, yeah, that's AJ times the vector Z minus epsilon AJW. But remember, we chose this W so that AZ times W is the 0 vector. So every row of this matrix, if you multiply it with Z, you get the 0 vector. So this part's 0. So this is just AJ Z, which is equal to BJ. So like, if that row is in A, then the constraint that we wanted is satisfied for X. Similarly, it works for Y. And then if it's a row that's not in AZ, then it's gonna work because of the way we chose the epsilon J's. And the epsilon is the minimum of all of them. So yeah, so if it's not in then we kind of win by the choice of epsilon. Okay, so and then the same thing works for Y. So, so yeah, this might be a little bit sloppy, but this is proving that X and Y are both in P. So this is one direction of the proof. But are there any questions about this? It's written more properly in the notes, but yeah. Okay. For the other direction, so now if we suppose Z is not a vertex of the polyhedron, so that implies that there exists X which is not equal to Y and lambda in the open interval 0, 1 with Z being equal to, these X and Y are in P, and there's some lambda where Z is equal to lambda X plus 1 minus lambda Y. Okay. So what I want to do is now find a non-zero vector in the kernel of AZ, and that'll, but again, by this rank nullity thing, that'll prove the theorem, or that'll prove this direction. So they'll prove that I want to get that the rank of AZ is less than n, so I just want to find any non-zero vector in the kernel of AZ. So note that for any row AJ of A that is in that is included in the matrix AZ, we must have that AJ times X equals BJ, and we must also have that AJ times y equals bj. Okay. That's not immediately obvious, but let's think about what if it wasn't? Like let's say, if let's say aj y is strictly less than bj, for example, without loss of generality, then if I took aj times z, well, by linearity and stuff, this is lambda times aj x plus 1 minus lambda ajy. And this one's less than this one because x and y are in the polyhedron. This one's at most lambda times bj, but this one's strictly less than 1 minus lambda bj. So it'd be less than or so we would have strictly, we'd have a strict inequality. And here I'm using the fact that lambda is not 0 and not 1, right? Because if lambda was 1, this would be just 0, but lambda is not 0 or 1, right? So I have a strict inequality. So this would contradict the fact that aj is in the matrix. So that would be a contradiction. But actually, because by this property, we now know that, actually, if you think about it, what this means is that if I take az times x, it's equal to az times y, because this means that the jth row of this thing is bj, and same with this one. So that means that az x minus y is the 0 vector, but x and y are not the same. So anyway, so that there's something, a non-zero vector in the kernel, so rank of az is less than n. Right, because x minus y is a non-zero vector, because they're not the same, which multiplies to 0, right? So, okay. Any questions about that? Okay, so that's how you classify vertices of a polytope. Okay, so we'll continue with this stuff next time.